Let me just have a very brief review of what I covered yesterday morning, and this is essentially where we had got to. We were discussing basic strategy which underpins the current range of algorithms which are being developed at various levels for working with matrix groups defined over finite fields. So the input we're thinking of is a bunch of matrices, a small collection generating set, capital X in this notation, and what we'll be thinking of doing as a first step, we're thinking of determining at least one of the Aschbacher categories in which this group lies. Thinking of a broad interpretation of what Aschbacher's theorem states so that it can be applied to every subgroup of GLDQ. And if there is a normal subgroup associated with the action of the group on the underlying vector space, then we're thinking of wanting to construct that normal subgroup N and working with N and working with G mod N. There's a word up here called recognize. I'll say a little bit more about what we mean by that as we go on today. And ultimately, what we expect to obtain as the output of this process is a composition series for the group. We may then want to do more work once we've obtained the composition series, and that's what I will also talk about today. Otherwise, if it's not the case that there's a normal subgroup associated with the action on the underlying vector space, then we're in these base cases for Aschbacher. So we're in the situation where G is either a classical group in its natural representation, or G modulo Z is contained in the automorphism group of a simple group. And as I suggested yesterday, at this stage, there's a step which is so-called reduction step down to a quasi-simple or a simple group L. I'm not going to say very much about that. If you really want to know what that is, it may be the case where G is a subgroup of the automorphism group of a simple group. And for example, I want to do derived group computations. There are good algorithms, for example, which can compute the derived group of a given group, and I'm thinking of having applied those to construct the L. And I want to name L, by which I mean I just want to know what I've concretely got. And part of that is a decision that will help me, guide me, in terms of the next step, which is how do I set up constructive isomorphisms between L and its standard copy. Okay, so let's go on from there. I already identified these. These are the base cases for Aschbacher. The classical groups to hang on to, which are big class, which we need to be able to deal with. And then we've got the other S or C9 list, other almost simple modulo scalars. Martin outlined a result yesterday, which is important in this respect, in telling us that the groups which lie in the C9 category are actually reasonably small. They're Q to the 3D at most, rather than Q to the D squared. So that's a significant drop in terms of the order of the group. Okay, so C8. C8 membership, I need to tell you about this because it affects the naming algorithm, the ability to know what the group is. And I'm using this notation SXDQ to mean any arbitrary classical group. So maybe SL, maybe SP, the orthogonal groups, etc. So the problem is, given a group G, sitting there as a bunch of matrices, can I decide whether it contains a classical group in its natural representation? Here I really am thinking of, I'm given D by D matrices, and I'm asking, does that bunch of D by D matrices, for example, contain SLDQ? That's the question which I want to answer. And this question played a fundamental role in terms of all that I've been talking about, and here I want to try and give you a little bit of the background of it. In 1988, at an Oberwolfach meeting, the very first held on computational group theory, Joachim Neubusser, who was one of the founding fathers of computational group theory, asked the question at that stage, can you give us an analog of an algorithm which exists to decide whether or not a group which contains, or which is sitting inside of Sn actually contains An? And there's a well-known algorithm where, based on a theorem of Jordan from 1873. The actual current version of the algorithm is in both Magma and GAP and is very widely used and was developed by Peter Cameron and John Cannon, I think in the 1970s and into the 80s. And it's based on this theorem, the content of which I'm not particularly concerned about, but I just want to tell you that what Neubusser asked for was an analog of this result, which says to you, if a certain condition is satisfied, then I can readily deduce that my permutation group contains An. And why is that useful? Well, we were talking about base and strong generating set in terms of a fundamental unit which we can use for working with matrix or with permutation groups. If you're talking about the group being AN or SN, then the base for the group is essentially the size of n. Its cardinality is size n. And that's not a very good situation. If you compare it with groups which are neither AN or SN, then the base is essentially tiny. People spend a lot of their lives in here and elsewhere proving that base size is typically 2 or 3 versus n. So there's a very big dichotomy between groups which contain AN or which are equal to SN in terms of their base size versus other permutation groups. And that was part of the way that this algorithm was used. What's typically done is at the beginning you say, apply this algorithm, deduce whether or not you've got a so-called giant. If you have, then you do something special for that giant. Otherwise, you use based on strong generating set machinery. Okay, so Neubuser was asking for an analog of this result, and it led on to a whole bunch of work, typically or principally started and developed by Peter Neumann and Charles Prager, which was the development of a naming algorithm, what is now what I call a naming algorithm. And underpinning this critically is this notion of primitive prime divisors, where we say that a prime R which divides b to the e minus 1, it's a primitive prime divisor of b to the e minus 1, provided R does not divide b to the I minus 1 for I strictly less than e. Okay, the key notion, there's a result of Zygmundi from 1892, which tells us that such primitive prime divisors exist except in very restricted cases. And why is this relevant? Well, think about what the order of GLDQ is. It can be written in this way as q to the d choose 2 times polynomials products of the type q to the I minus 1. And what that says to you is that PPDs of q to the e minus 1 for various values of e at most d actually divide the order of GLDQ. And also, if you look at the formula for the orders of classical groups, you've got the same essential structure turning up. And that leads us to the notion of a so-called PPD element, which is an element whose order is a multiple of some primitive prime divisor. Okay, going back to the naming question, this was the question we were asked, given a bunch of matrices of dimension d, does it contain a classical group in that dimension? And Prager and Neumann, and then some years later, Prager and Niemeyer gave some beautiful algorithms which answer this question very precisely. They give you Monte Carlo polynomial time algorithms to name the classical group in the natural representation. So to tell you the answer, whether it's yes or no to that question, and to identify precisely what is the classical group that's contained within the group G. Excuse me. The algorithms are really were the epitome of high-quality, well-analyzed algorithms at that stage. And they remain the paradigm for how you could get excellent analysis, which tells you a great deal. It wasn't just the work which was done by Neumann and Prager, which was fundamental, but it was also the ideas of exploiting Aschbacher, the whole notion of exploiting the theorem of Aschbacher to help you to develop algorithms for linear groups. It is buried within the work of Prager and Neumann very explicitly. Excuse me. Again, what goes on is that they search for certain kinds of PPD elements that occur with high probability in classical groups and are only in a small number of other groups, subgroups. And what they do then is, once they find some, they can rule out the small number of other subgroups. It's a Monte Carlo algorithm. It's essentially saying to you, if you do discover these elements, then you're guaranteed that it contains the classical group. If you don't discover them, there's a small probability of error. You've made a mistake. But what really shone a very strong light on an approach was the fact that they got very, very precise estimates, and they got incredibly efficient algorithms. We're talking about log D searches to decide the question. If you think about log D is, it's very tiny. Okay, that was very much within the context of natural copy matrix group. You can also ask the question, of course, and it needs to be answered in the context of black box groups, in the context of a permutation group or some other representation, be it in defining characteristic or be it in cross characteristic for the matrix group. And To answer that, there's a very nice paper of Babai, Cantor, Palfy, and Scheres, which give you an essential answer to this question. So given a group G isomorphic to a simple group of Lie type of known characteristic, its standard name can be computed using the polynomial time Monte Carlo algorithm. The actual technique is essentially a generalization of ideas from Prager and Neumann. You're choosing a sample of nearly uniformly distributed random elements, and what you're doing is you're reading off PPT information from them. And what you're doing is you're finding the three largest integers, these VIs, such that a member of L is ordered divisible by a primitive prime divisor of one of these. From this, you can deduce so-called Artin invariants, which are sufficient to actually tell you that within this group G, you've got some copy of SL45, PSL45, PSU, 6, 7, etc. sits inside of G. And then these three names, or these three values, typically determine G in the name. There was one very hard case, which was sorted out by Alzheimer and Borovic, where PPD information essentially is not sufficient. And that was also important in terms of the first time within this project that centralized involutions were used. They had been used extensively by people before, but within the context of the matrix recognition, this was the case where we started using them. Okay, so that's what happened on naming. We're in a pretty good position. I mean, you need to add on to this recognition naming for AN and SN, of course, and for sporadic groups. And that's also available. And it gives you the ability to be able to name the group. More correctly, to name the non-abelian composition factor of the almost simple group. Okay, one part of that was that there was an assumption that we knew what the characteristic was. In the statement of Babai et al., we're talking about known characteristic. And so the problem is the following. It's almost a precursor to sorting out the Babai et al. Application, is to decide whether we can determine what the defining characteristic is. And there's a theorem of Martin and mine from 2007. In fact, it was our first collaboration. It was the point at which I turned Martin into a dangerous example of somebody dabbling in computational group theory. As a referee for one of my grant applications, suggested I had misled him by dragging him down a dangerous path from which he has never quite recovered. In any case, that referee may well be in the audience, by the way. I mean, I have no idea. But here we are. We get a black box polynomial time Monte Carlo algorithm to determine the characteristic of a quasi-simple group of Lie type, subject to the existence of an order oracle. In fact, the order oracle is for SL2Q, but you can just get by with just the order oracle for G as a whole. Okay, and the key idea here, again, we use the centralizing involutions. What we do is we come down through centralizing involutions to find a copy of SL2 in defining characteristic. And once you're down to SL2 in defining characteristic, you then read off what the characteristic is from that copy of SL2. Okay, there is an alternative from Cantor and Scheres, which was a version for matrix groups for absolutely irreducible matrix groups. This was black box and is implemented as a black box algorithm. Works very happily for permutation groups, for matrix groups. This is very much for absolutely irreducible matrix groups. Okay, so we're now at the stage where I can talk about, we know the name of the group. We've come down to a base case and we know what the name of the group is. So we know that it's J1, we know that it's PSL 6,5, we know that it's E6 of 3, etc. And now what I want to talk about is how do we work with that? How do we actually write down good machinery for working with that group? And the real question which I want to address is, how do we set up sensible isomorphisms between that group which we've discovered, a copy of the group we've discovered, and a nice copy of the group, which I think of as the standard copy of the group. So here's a situation we're in. We have C, a standard copy of some group. We talk about it as the gold copy. And I've got G given to me, and the only piece of information I know is that G is probably, with high probability, isomorphic to C. I am deliberately and not carelessly using different labels for generating sets. If I had the same generating set, there wouldn't be an issue. So I am simply stating, here's C with a generating set X, here's G with a generating set Y. I know no relationship between them. I do know from my naming, I'm sorry?
In the second line, the standard copy, is it C or G?
It's C. That's why I say C is the standard copy. Otherwise, I would have said G is the standard copy. Sorry, Garrett. Okay, C is SL65.
C is your matrix group given.
No, I'm sorry. I have changed. C is my standard copy. Think of C as being SL65, 6 by 6 matrices. I give you some representation of SL65, which is my group G. I'm sorry, the confusion may be about X and Y. That I was using X, yeah, okay, all right. So I want to construct effective isomorphs from C to G and from G to C. The people who've never worked with an algorithm in their lives and are not going to may well be distressed by my trying to talk about isomorphisms in both directions, because they may well feel, well, you've got an isomorphism, what's the fuss about? Well, the reality is I want to be able to go from C to G, and I want to be able to go from G to C. So I'm making a fuss about that ability. Okay, and the key idea is to use standard generators, to write down a generating set in C, to write down the equivalent generating set in G, which allows me to define the isomorphism. Okay, let me illustrate it graphically. Let me take C generated by X. This is my gold copy. I don't know whether it's very gold or not. It looks very yellow to me, but there we are. For those of us, so C is given to me. I can write it. I can choose X. I have a lot of control over X. And sitting over here, God, that's even more bizarre. I don't actually know what color that is. It certainly isn't the color which I chose, I can assure you. But I'll blame it on technology. Yes, fine. So here's my user-supplied copy with a generated set Y. What do I actually want to do? I want to set up an isomorphism between C and G. One way of doing that is that I find some standard generators in C, some system of generators in C, which I call standard generators. And I want to find them as words in X. That's my task. And I want to be able to also find the same standard generators in my group G as words in Y. And once I've done that, then to define an isomorphism is straightforward. It's just the extension from S to S bar. Okay. I'm not saying anything here. All I'm saying is how I could realize my isomorphisms. That's all. My second task is, if I have an element H, which I can write as a word in S, then if I want to actually realize what its image is over here, well, all I have got to do is I've got to take H, which I know is a word in S, and I simply evaluate in S bar. And now I can write down what H bar is here, the image of H under my isomorphism phi. Okay, so I can set myself two tasks. One is find standard generators in both copies as words in the defining generators. And secondly, given an element in S or given an element in C, I want to be able to write it as a word in X. And then I can just take that word and evaluate it over here. And if I want to go from G to C, same task. If I take H bar here, and if I could write it as a word in S bar, I could literally just take that word and evaluate it over here. This is elementary. I'm not suggesting there's anything deep here. All I'm doing is illustrating what the tasks are that I need to be able to resolve. I've identified two tasks. One is find standard generators in terms of X and Y, and secondly, be able to write elements as words in those standard generators. Those are two independent pieces. If I can do them, then I can actually have an ability to move between both copies. Why am I making the fuss about words? I'm making the fuss about words because ultimately I want to use all of this machinery to answer the membership problem. The membership problem is if I have something sitting in the generic copy of C and I want to know what it is as a word in X, my input generator, the input generators, then I want to be able to write it first of all as a word in S. I know what S is as words in X, and hence I can write H as words in X. Okay. All right. So that's the framework of trying to exploit standard generators to get isomorphisms between effective isomorphisms in both directions. Okay. Let's look at an example of this for standard generators for SLDQ. Much of this work which I'm talking about is joint work with Charles Leighton Green, who's been my long-term collaborator on most of this over 25 years at this stage. In 2009, we wrote down standard generators for classical groups in odd characteristic. Okay, here's the full list of standard generators. We want to take 4 standard generators for SLDQ, 3 of which lie down in a copy of SL2Q, and 1 additional one, namely V, which acts as the D cycle. The reason for the signs is to ensure that the appropriate determinant condition is satisfied. Okay, it's quite important to observe I'm taking 3 of these lying down in SL2Q, and only 1 of them lies outside of that small group. So that suggests that if I could come down to SL2Q, I might well be able to produce these 3 generators and just pull them back through the group in some way, and then all I've got to do is produce my D cycle at the end. Okay, there's always I, as the developer of the algorithm, have the right to make a decision about these. I can choose these. I could choose these to be sensible, well-chosen algorithms, which will well-chosen generators, which will facilitate everything else I want to do. They're not dictated by anybody else. Okay, and part of what drives this decision is I want to be able to do echelonization in a sensible way. I want to be able to write an element of SLDQ as a word in these 4 generators. Well, this is the sort of task which you give to undergraduates, and they do very badly in terms of echelonization and in terms of working out what rational forms of matrices are. It's pretty straightforward for a machine to do it, however. Okay, so let me outline the basic algorithm for finding such standard generators within some copy of SLDQ. I'm going to present it as if I'm given the natural copy, because it's much easier to visualize it in the natural copy, but in fact, we don't care. We really want to be able to do it with any copy of SLDQ. And so what we do is we're given as input G, which we guess is isomorphic to SLDQ. We want to produce these generators. Okay, so what I do is I want to construct 2 subgroups, H and K, which with respect to a basis, and if we're thinking of it as a natural copy, they essentially commute. They commute. H is effectively SLM, and K is effectively SLD minus M. For the purist, I'm paying no attention to centers. Centers may have disappeared. Much of what I'm talking about may be modulo centers, but for the sake of exposition, it's much easier to assume they're there. Okay, and observe that H acts on SLM, K acts on SLD minus M. I haven't told you how to construct that or anything else. I'm just saying, suppose I can construct it. And now I'm going to say, well, recursively, I've now got down to an SLM. And so what I'm going to do is I'm going to recursively construct standard generators for H and K. All right. Well, among the standard generators for H are the 3 generators sitting in SL2, which I mentioned a few minutes ago. And so all but the cycle from the standard generators for G are contained in SH. And so all I'm left with is to actually deal with producing the cycle. Well, I've got 2 cycles. I've got cycles coming from H, and I've got a cycle coming from K. I've got an M cycle coming from H. I've got a D minus M cycle coming from K. And now what I want to do is put them together in order to produce a D cycle. Well, multiplying them together won't get me a D cycle. But if I can find another nice, well-behaved element, then I will be able to multiply them together. You can do this in permutation group context, which is where all of this started life. You take your cycle in SLM, you take your cycle in SLD minus M, and you think of a little element, a gluing element sitting in here, which acts on the last 2 elements of this basis and the first 2 elements of this basis, and which just simply does an interchange. And now multiply them together, and what you produce is your D cycle. Okay. Why am I making a fuss about certain things? I'm making a fuss here about M being approximately D over 2. Why? Because I want to come down to the bottom. I want to come down to dimension 2, or an SL2, in log of these steps. So I want to break the problem recursively as quickly as possible. That's part of the reason for choosing to break it in that way. I haven't told you at all how to construct these. At some point, however, some work has to happen. You have to actually do something. All I've suggested so far is you do a recursion. When you get down to an SL2, and within an SL2, you've got to find your standard generators, your 3 generators for SL2. And then you've got to pull them back, etc. Okay, so it means that this idea, there's a lot of work to actually realize the idea. I've presented it for SLD. You can take that idea and generalize it to other classical groups, generalize it from odd characteristic, where it's significantly easier, to even characteristic, and you can generalize it from the natural copy to the arbitrary representations, to black box representations. And out of that, you get a theorem which says the following. It says to you there's a Las Vegas algorithm, which takes as input the group G with some generating set, and it returns standard generators S for G as words in X. And with due apology to Gerhard, because this is where the confusion, I think, is partly from about X versus Y. Here I'm thinking of the group is given to me with X, and I want to return standard generators as words in X. Nice thing is the algorithm's complexity, OD to the 4th. If you're thinking of what the cost of matrix multiplication is, it's D cubed. The cost of computing the order of a single matrix, I was talking about yesterday, is effectively D to the 4th. The fact that we have algorithms which are finding standard generators in time D to the 4th is pretty good. The reality is this D to the 4th has actually dropped because of the hard work of Schreier-Prager and a bunch of other people since then. So in effect, the complexity of the algorithm is closer to D cubed log D, which is pretty remarkable. Again, there are similar approaches which can be done for exceptional groups. I wish that the one line was reflective of the amount of work which was required to achieve that one-line theorem. I think Martin even would regard that the fact that we spent 3 months working on this non-stop was reflective of a lot of investment of effort. And I don't mean to belittle it by giving it one line. But the reality is we've done similar things. You can define standard generators, you can define and exploit the algorithms which come out of this work in order to give you this theorem. There's a whole bunch of people mentioned up here, some of whom are in the audience. Of course, Charles and myself, but also Frank Lubeck and Heiko Dietrich. And the reason for 3 different papers is there's odd characteristic, there's even characteristic, and finally there's a black box variant. I should also mention that Heiko Dietrich is going to be here at the end of the month as part of the computational algebra workshop, and he's going to spend his entire lecture talking about what I just talked about on one transparency. You may even see that transparency again, but you'll see an awful lot more of the detail of how you do that. Okay, so we've got to the stage now where we can find standard generators in classical groups, exceptional groups. They're for the remaining exceptional groups. The remaining exceptional groups were dealt with by Henrik Barnheim and John Bray and a bunch of other people. Henrik Barnheim was a postdoc with me, a PhD student with Charles Leadham Green, on Suzuki and on small and large regroups. Okay, that's finding standard generators. Very much underpinning all of this is the notion of centralizers of involutions and statistical group theory telling you about how hard you've got to work. That will actually form much of what Heiko will talk about later in the month. Okay, that was one part of recognition. The other part, just to mention them, there's a beautiful work of Jambor and Niemeyer and Pleskin, and I think one other person dealing with AN and SN on constructive recognition algorithms. And of course, the whole notion of standard generators, the whole notion of black box algorithms for finding them dates back to the work of Rob Wilson from the 90s and others in Cambridge in the 80s and 90s. But Rob even coined the term standard generators in the 96 paper. You're denying this, are you, Rob? Yeah, I can point. Well, certainly you have a paper which is talking about finding standard generators for sporadic groups. Okay, so that gets you standard generators. It doesn't solve the second problem which I identified of how to write elements as words, and I'll say a little bit about that in a moment. I just want to mention the fundamental base case, SL2Q. There is a paper of mine with Marston Condor and Charles from 2006, which gives you an algorithm which works with SL2Q. What's the problem with SL2Q? The problem is that the proportion of P elements drops off as 1 over Q, and you need to find a transvection. So you need to find an element of order P within SL2Q. It's not a case of writing it down. I need to find it as a word in the defining generators. And that's the hard problem, because if you're not careful, your search will drop to O of Q search. And if Q is large, you simply won't find anything. And by large, I really just mean about 5 to the 6, 5 to the 7, that sort of order of magnitude. We're not talking about on the edges of the universe. We're talking about reasonably small fields where it's hard to find a transvection by simple search. And therefore, you have to do much better. We came up with a better approach, which uses the discrete log oracle in a paper in 2006, which is actually the practical algorithm. But there are two other approaches, Cantor and Kasabov and Borovic and Jelenka, which give algorithms for this task without the use of that oracle. I have reservations about the claim that you don't need the oracle for SL2Q and odd characteristic, because I can't see how you still avoid the use of the oracle, but that's a quibble about things. Okay, the other critical base cases are SL3Q, SU3Q. Here, let me also mention that Kai Magard was very actively involved in SL3Q. Kai played a very fundamental role in pushing a number of us to take on some of these. Frank and I collaborated with him on SL3Q, and he was fundamentally important in terms of driving people to answer certain fundamental base cases. I realize my notes don't actually say anything about the question of rewriting, because I seem to have deleted it at some point in preparing this talk. Let me mention, however, that we do have algorithms, excellent algorithms, which deal with the writing of elements as words in standard generators. Those come about from a variety of sources. Elliot Costi, who was a PhD student at QM in the 2000s, he wrote natural copy code, which means if you're in the natural copy and you want to write an element as a word in certain prescribed generators, you could do that very effectively. Much more important work by Csaba Schneider has basically solved the problem for classical groups in general. And in terms of exceptional groups, the real solution is, our practical solutions come from work of Don Taylor and Aria Cohen, which is a development of stuff which they did first of all in the early 2000s, and which by virtue of me standing over Don for 5 years has finally reached an endpoint. And we've actually produced beautiful code which does that extremely rapidly based on these generators. Okay, let me turn to the question of verification. I stated that we have a Las Vegas algorithm, that actually this whole process gives you a Las Vegas algorithm to get an isomorphism between your input classical group or your input group of Lie type and your natural copy or your standard copy. How do you get that? You get that by means of verification. Here's one part of it, which has a publication date because it's finally appeared after about 14 years of hard work. It's finally appeared. A statement along the following lines that every classical group of rank R defined over GFQ has a presentation of length O of R plus log Q on its at most 8 standard generators. So there's at most 8 standard generators. Number of words in that statement. What do we mean by length and why do we care? If you want to think about length, think of literally writing down the presentation and seeing how many characters you need to write down the presentation. Why do you care? You care if, for example, you took SL 20,5 and you have an isomorphism which you want to verify. If you have d squared relations, you have to evaluate those d squared relations in matrices. Then what you end up with is you end up with d squared times d cubed as the complexity of verification. I was boasting over the fact that we're really good at constructing standard generators, etc., in time d to the 4th. And suddenly I'm saying to you, well, to verify the fact that we've got this isomorphism will actually take me d to the 5th. I don't want to spend more time on verification than I want to spend on constructing the isomorphism. So therefore, it led people to believe that there would be good merit in having short presentations, where short is really a synonym for controlling the number of generators that you have, the number of relations you have, and the so-called length. So how many exponents turn up in it, etc. And that's what led us to get this result of O of r plus log q. It's not the optimal result, and I'll explain why in a moment. But let me also say that in the context of exceptional groups, what we're actually using are reduced Curtis-Steinberg-Tietz presentations, because standard generators for exceptional groups were literally taken to be the generators which satisfy these presentations, which made it very easy to actually use these presentations later. And of course, John Bray and Rob Wilson and the whole crew who have been around for years working on aspects of this very successfully give us presentations on standard generators for sporadic groups. You may be, well, let me just make this point. If you want to verify, what you do is you take your supposed standard generators in your copy, you evaluate them. If it turns out to be the identity, all relations are satisfied, then you've got your proven isomorphism. It doesn't matter what you've done along the way in terms of whatever heuristics you've used, etc., whatever decisions you've made about types of algorithms. If you get to this stage and you can verify that the relations are satisfied, then you've got an isomorphism. Okay, you may well be struck by the absence of AN and SN from this page. Yes, there's a reason, which I will justify in one moment. Let me just make the following comment. There's 4 authors, Goranlik, Cantor, Kasapov, and Lubotsky. Sorry, for some reason there was a complete breakdown about, of course, one of the fundamental components which allows you to write down short presentations for groups of Lie type are the question of what kind of presentation you have for the Weil group, be it SN or AN or sign permutations, whatever you're including. You need to care about what the type of presentation is and what the length of it is in terms of wanting to get an optimal result. The optimal result for SN, I'll state in a moment, but let me just mention this very nice statement coming from GKKL, which says to you that if you want to choose as your generators for SN, the 2 generators which we know and love, namely a 2-cycle and an n-cycle, then it is the case that the shortest presentation has the length n log n. You can't do better than that. And those are the generators which we actually use for SN and for relatives of it in terms of writing down the presentations for the classical groups, and hence the reason why we have an R rather than a log R turning up. So we stay with this. What Goranlik et al. Managed to do is they produce for you a 3-generator, 7-related presentation for SN on your 2 favorite generators, plus one other rather indeterminate generator, which is, with great effort, resolved as a word in A and B, and then it has length O of log n. I don't mean to dismiss this in the slightest. This is an incredibly beautiful result, which says to you that you can bound absolutely the number of generators and the number of relations, and you have length which is optimal, because you cannot even represent n by fewer than log n bits. So therefore, this is absolutely optimal. Having said that, having showered much praise on the result, I can also point out that 4/7 of the result has a bug in it. And the 4/7 is a very precise statement in the sense that of the 7 relations, 4 do not evaluate in the group. So one of my honor students has actually provided a corrected version of the presentation. Well, I should admit that he's now at the University of Chicago, which probably explains why he did manage to actually sort out what GKKL were putting forward. Also, the actual generators are resolved, everything else. And it ends up as being a very nice piece of work. Okay, I also want to make a different comment, and in practice the whole thing is irrelevant. And the reason why the whole thing is irrelevant is the following, that I want to solve the question of writing elements as words in input generators. So I really want to be able, given X as the generating set, I want to be able to write elements as words in X. How do I do this? I find standard generators as words in X, and then I write an arbitrary element in terms of the standard generators, and now I evaluate to get back to X. Well, if you think about this, what this actually says to you, if you're given Sn as X for a moment, then we need C as a word in X in order to be able to proceed. Now, what's its length? Well, its length is n log n, because that's the diameter of a graph in an arbitrary generating set for Sn. So I'm afraid that I'm reaching the point where I regard the shortness and various other criteria as somewhat irrelevant, but beautiful mathematics, but not particularly relevant from the recognition point of view. But what we do have at the end of it are presentations, generators, etc., which actually do allow us to get a statement which is Las Vegas. Okay, composition tree. Composition tree is something which actually pulls all of this together. It exploits the geometry and constructive recognition to get us a composition series. This is what the structure of the tree looks like. You're thinking of taking a node, which is the section H of G. You have an image, and you have a kernel. And we think of it as a tree structure. We end up with leaves, which are composition factors for the group. The development of it basically dates back to work of Henrik Barnheim with Charles and me and Derek Holt, who's been absolutely fundamental in terms of actually getting this to the stage where it all works. It's publicly available in Magma. I know that there are parts of it which exist in GAP as well, and hopefully more of it will be available in GAP in the future. Okay, briefly to state what the output of composition tree is. The output is a composition series, a representation of the composition factors. You get effective maps from GK to SK and from SK to GK. And most critically, you get a map to write an element G of X as a word in capital X. And if you hand in, if you're thinking of G as a matrix group sitting inside of GLDQ, you can also do membership testing, in the sense you take an element of GLDQ and you say, does this lie in G? If it does, tell me what it is as a word. You go through that process and you either produce false or you produce the word. Okay, so that's the data structure which you're getting out, which I think of as the analog of base and strong generating set. Base and strong generating set told you what the order of the group was, and it told you about membership in the group. It allowed you to solve the membership problem. What composition tree does is effectively the analog of that for linear groups. Okay, and if you want to turn the whole algorithm into a Las Vegas algorithm, once you have the ability to write down presentations for the leaves of the tree, for the composition factors, then you can actually do a very simple procedure to produce a presentation for the group itself. And what you do is you just verify that the group satisfies these relations, and if it does, you've got a Las Vegas algorithm. So you learn the composition factors and you learn them in a Las Vegas manner. Very recent result is the following. It's so recent that it's still with a referee who might indeed be in the audience also, in which case I apologize if I've said anything offensive to that referee. It's perhaps a bit late to worry about it now, but let me try, in any case, to redeem myself. So, subject to the existence of a discrete log oracle and an integer factorization oracle, there is a polynomial time Monte Carlo algorithm which takes as input G and constructs its composition factors. And note, you may well be surprised at the fact that we can get this result, given the fact that yesterday I admitted that we cannot resolve C4 and C7 membership in polynomial time. We get this by a variety of skilled obfuscation and avoiding going anywhere near those two categories. That's essentially what it boils down to. And it was so skilled obfuscation that it took about 3 years for Charles to convince us that there was any content in this theorem at all. And in fact, we spent a long time debating whether or not there was a theorem or whether it was just one of those myths which Charles sometimes is renowned for producing. In any case, we can upgrade to Las Vegas for everything except twisted G2 of Q. And the experts, such as Mr. Kasabov at the back, will be fully aware of why we can't upgrade, because we haven't got a short presentation for twisted G2 of Q. So that's something which would be very nice to actually get, even not necessarily short, but even getting a useful, effective presentation, which actually could be used, would be very helpful. But we do get Monte Carlo, and if you ignore that case, you get Las Vegas. Okay, so that's a good situation. Before, however, I get too carried away about it, I should point out there was a black box model for doing entire computations in matrix or in linear groups developed by Baba and Beals, which essentially got to the same position some years ago. It's just that nobody has ever tried to develop that, and I don't think from a practical point of view that it will ever be actually realizable, but they did get exactly the same result, subject to discrete log and subject to integer factorization. The integer factorization comes from the order question. The discrete log comes from a variety of sources, including SL2Q. Okay, so let me try and wrap up by talking a little bit about what can we do with the output. What we can do with the output is to we use it as infrastructure for the soluble radical model of computation. This is intended as a uniform approach to computations with linear groups. And what we're thinking of having got is an analog of Schreier-Sims data structure for permutation groups. I want to discuss very briefly the soluble radical model. This goes back to a notion that finite group G, it has a characteristic series of subgroups where O infinity is the soluble radical, where S star modulo infinity is the socle of G modulo the soluble radical. It's a direct product of finite simple groups, non-abelian simple groups. And then we've got permutation action where we've got we've got a mapping from G to the symmetric group of degree K, where K is the number of non-abelian simple factors turning up here. And we've got the P of G is the kernel of phi. So within every finite simple group, there exists, within every finite group, we have such a characteristic series. And what composition tree allows us to do is it allows us to construct this series. It allows us to set up the machinery for this series and to work with the components of it. Okay, and of course, using Schreier's conjecture and the classification, you get that P of G modulo S star of G sits inside the direct product of the outer automorphism groups. And so it's soluble itself. Okay, so that's the basic structure of the soluble radical model that you want to exploit that series. And where does the realization of the effectiveness of this come from? It comes mostly from work of Cannon and Holt from late 1990s and into the first part of this decade, where they use C and variance in terms of practical algorithms. So I'm using C as just the name for this characteristic series. And what they also do is, of course, they simply write down a chief series for L, and so you end up with a series which is refined and which has elementary abelian components in it for L. Okay, so the soluble radical model says to you, you end up with this series, and if you're given a problem, whatever the problem is, such as tell me about the maximal subgroups of G, tell me about conjugacy classes of G, tell me about the character table of G, etc., then what the hope is that you solve the problem first in G modulo L, and then you lift it through the radical series. And you hope, what you really hope is, whatever problem you've asked, it has a nice solution for G modulo L. So it has a nice solution for H. Okay, so that's the hope. I mean, this is sometimes called a trivial fitting series also because H itself has a trivial fitting subgroup. Okay, and in many cases, what's easy to do is to reduce whatever the computation is for the trivial fitting group H to almost simple groups. Let me mention a couple of examples or some examples of this. One is determine conjugacy classes, determine maximal subgroups, determine automorphism groups, determine conjugacy classes. Let me just mention, you can see Cannon and Holt and their collaborators are the people who've mostly worked on this. You may well say, well, all of this predates composition tree. Yes, it does, because what they did was they developed things in a sensible way, which exploited whatever data structure was available to them. And Derek has spent a number of years since then exploiting other variants which allow us to answer the necessary questions. And amazingly enough, those necessary questions are membership and order and such like. Okay, so for example, on consciously classes of elements, this is a pretty good example in terms of what can be done and what has been done. There's work, of course, for Tim Wall, and there's work of Gary and Martin, which give you consciously classes and centralizes of elements of classical groups. What we've been trying to do is to make that quite explicit in the sense of being able to list explicitly consciously classes, centralizes, and the ability to do conjugation within the group. And that's been worked with Samuel Gonshaw, who was a student of Martin, where we've given an explicit listing of classes of unipotent elements. And Martin and I have an ongoing project, which has now been ongoing for a little bit too long, Martin, so we're very optimistic that while we're both here, we'll make progress on sorting out the rest of it, which is really the hard part which is left, is on consciously testing. We've written down centralizers, but we need to sort out some things. All of that has been dealing with unipotent elements. One of my PhD students, Giovanni De Franceschi, has taken all of this and actually sorted it out for semi-simple elements and also sorted it out for mixed type elements subject to our work for the unipotent case. So in effect, given D and Q, write down consciously classes in SL 100,5 if you're daft enough to do that. More realistically, if you take some element of SP 64.8, you can compute its centralizer explicitly. If you're given two elements of that group, you can decide whether they're conjugate. And literally, I mean, in the sense of some seconds of work is where it is. Okay, that allows us to answer such questions within an arbitrary representation of the classical group. A good question to ask, given the experts here, is that it would be nice to do this exactly the same thing for exceptional groups. And I think I'm getting to the stage where I seem to be able to persuade some people that that might be a realistic project to actually carry out. And if you want to go the rest of the way, it's not very hard, not very hard to state at least. I'm not saying that it is trivial to actually develop all of the necessary machinery, but if you want to do it, you now are able to embed H, which is G modulo the soluble radical, direct product of these automorphisms or these Reith products, and you can use work of Alexander Holtke and Cannon and Holt to solve the problem within Reith products, and then you can actually lift everything back through. And in fact, it's essentially been done by Cannon and Souvigny as long ago as 1997, and Alexander Holtke in a much more recent development, which Alexander might actually be talking about also at the end of the month at the computational workshop here, which is to use the soluble radical model to pull the information back. Okay, let me wrap up with one other very quick example, which may be of interest to people here, which is Bill Unger's algorithm, which is in Magma for computing character tables. I'm not going to spend the time on talking through it, but essentially what he's doing is he's producing a large amount of elementary subgroups, and then using Brouwer's theorem and induced characters to build up a full list of characters, and then using the triple L algorithm to produce a basis for the Z module of generalized characters. And from that, being able to extract the irreducible characters of the group. He's actually developed a version which exploits composition tree, and that has shown immense improvement over existing versions because of the fact that you can exploit the ability to decide membership and to write elements as words. There's one very simple example of that. I mean, this was a question which was posed to me some time ago, which I did about 20 years ago, 2 to the 30 L5 of 2, where it took some months to compute. Now it's down to a few hours. So it's not, it becomes a very feasible computation. These are some other examples where you can actually just literally do it very routinely. There was a project which I was involved in with Thomas Breuer and Gunter Mahler, where we've actually used all of the machinery in Magma to verify the character table in response to the doubts raised, or the atlas in response to the doubts raised by J.P. Sayre about the correctness of character tables in the atlas, and those were done completely directly, completely hands-free in some sense for all but 4. The 4 which are listed, I think, are those, and all but M is now verified. Is that correct, Rob? I know there's a paper of yours which is dealing, is that already dealing with M or not? Dealing with Baby Monster? Baby Monster, okay. So all that's left is M. And I know that Kai McGard, again, one of the great losses, that Kai had grand plans for how to pursue that. Let me finish by identifying that while we've made immense progress, not everything is yet finished, so I can't actually just give up and go home. Here's a few other challenges that would be interesting. Exploit the excellent work of John Bray and Colva and Derek to get maximal subgroups of all groups and actually use the soluble radical model in that way to write down maximal subgroups of all groups. And of course, you could link into what Martin was talking about in terms of the explicit classifications for exceptional groups. That's something that has not been done as far as I'm aware. I know that Derek may be skeptical about its value, but it would be interesting to see as to whether it could be actually developed effectively. Here's a hard problem, and I know that Charles is going to be here at the end of the month, and Charles is going to announce to you that this problem is solved. And that is actually Charles's eternal optimism. And my job in life, in collaboration with Charles, is to tell him that 10 years from now, we'll have solved this problem. I can tell you that we've made interesting and genuine progress, much more than I expected to. And that's an optimistic statement from Eamonn. But I know that Charles is going to regale you with the fact that this problem is now finished and we can give up on it. It's not quite. It's a bit like the table which Martin was talking about yesterday that Kai McGard used to have. It's a bit like that table, because what we're doing is we're playing games of saying CI intersection CJ, where you have a subgroup in the Aschbacher class CI and you want to intersect it with CJ. The only case which is definitely finished is C8 intersection C8. That's the only case which is absolutely finished. So that leaves rather a lot, 9, choose 2 minus 1, as the number of cases left. And Charles believes, because we've dealt with 3 of these, that we're finished. But, you know, optimism is a good thing. And, of course, I can't finish without mentioning my favorite hard problem, which remains outstanding and where we're not making any progress by any of these means, and it is, I give you a subspace of the underlying vector space, and I say to you, tell me the subgroup of G which fixes that space as a space. That has profound applications. I would love to make progress, and sadly, there's almost nothing which I've talked about in the 2 lectures which have helped in that direction. There is work which James and Wilson and Peter Brooksbank and others have been involved in, which is making contributions and where composition tree helps in terms of computations, but it is not getting us to a stage where we could be optimistic about dealing with D equals 10 and Q equals 5, let alone the ambitious targets of 100 and 5 to the 10, which I set at the beginning of my talk. Thank you for your time. Indeed. It would be a very fitting tribute. Thanks.